Common examples of moment of force. To open or shut a door, we apply a force F normal to the door at its handle P, which is provided at the maximum distance, as you can see in the picture 1.5. We see that if we apply the force at the point Q, that much force is required to open the door. If the force is applied at the hinges, we will not able to open the door itself. Same time, if we are applying the P force at the point where it is provided near the free end, the door, so that smaller force at a larger perpendicular distance from the hinges produces the maximum moment of force that will make easy to open and shut the door. Next here, for turning a steering wheel, which is shown in the picture 1.6, a force is applied again tangentially on the rim of the wheel, so that force is applied at the point A of the wheel. The wheel rotates anti-clockwise. The wheel rotate while in 1.6b the wheel rotates clockwise direction. Now here next is bicycle. To turn the rear wheel anti-clockwise, a small force is applied on the foot pedal of a toothed wheel of a size bigger than the rear wheel, so that perpendicular distance of the point of the force of application will be maintained. Like that, 1.8 diagram, spanner used to tighten or loosen a nut has a long handle to produce a large moment of force by a small force is applied normally at the end of the handle. The spanner is turned anti-clockwise to loosen the nut by applying the force in the direction, while in turn clockwise direction to tighten the nut by applying the force in a direction opposite to the nut. Like that, a jack screw also is used to lift a heavy load such as vehicle has a long arm. Like that, here we have to take up kinds of equilibrium. Equilibrium is of two types: static equilibrium and dynamic equilibrium. Here, static equilibrium, when a body remains in the state of rest under the influence of several forces, then we say static equilibrium. On the other hand, when the body remains in the state of motion, might be it is translational or rotational, under the influences of again several forces, the body is said to be in dynamic equilibrium. Example here, book lying on the table. For the static equilibrium, if a book is lying on the table, the weight of the book exerted on the table vertically downward will be balanced equal and opposite force of reaction exerted by the table on the book vertically upward. Thus, the book is in the static equilibrium. In a beam balance also you can take up, when a beam is balanced in a horizontal position, the clockwise moment of force due to the object on its right pan balances the anti-clockwise moment of force due to the weight in the left pan. The beam has no rotational motion, then you can say it is a static equilibrium. Now the example, dynamic equilibrium. A raindrop reaches the earth's surface with a constant velocity. Here the weight of the falling drop is balanced by the sum of the buoyant force and the force due to friction of the air. The net force on the drop is zero, so it falls at constant speed or a velocity. Like that, an aeroplane moves at a constant height when upward lift on it balances its weight downward. Another example, a stone tied at the end of a string whirled in a circular path with a uniform speed in a dynamic equilibrium, because the tension in the string provides the centripetal force required for the circular motion. What is centripetal force? We will come to know in the next exercise. So the examples, when we compare here almost the static equilibrium, all the examples we compare for the rest position. Dynamic equilibrium we take up for the motion in the body. Here in the rest, the book will be having the same force acting downward on the table, and the table also apply the force on the upward. Now another dynamic equilibrium, a raindrop reaches the earth's surface with a constant, because all the force which is already the raindrop is in motion and acts on the forces, means frictional force might be, and the weight force or any buoyant force is acting, all will be zero. Next we'll move on to condition for equilibrium. Here from the above examples we can come to two conditions, that is, number one, the resultant of all the forces acting on the body should be zero. That means when you add all the sum of all the forces, might be the body is in motion or state of rest, might be all the forces acting on it, it will be total forces will be zero. That is number one. Number two, the algebraic sum if you do for the moment of all the forces acting on the body about the point of rotation again should be zero. That means the sum of the anti-clockwise moment about the axis of rotation must be equal to the sum of the clockwise moment about the same axis. Based on this equilibrium, we'll move on to principle of moment. What is principle of moment? When several forces act on a fixed body, it will tend to rotate about an axis passing through the fixed point. The resultant moment of all the forces about the fixed point is obtained by the algebraic sum of the force acting at that point. To find this algebraic sum, the clockwise moment is taken positive and the clockwise moment is taken anti-clockwise moment is taken as positive and clockwise moment is taken as negative. According to the principle of moment, we can say if the algebraic sum of the moment of all the forces acting on the body about the axis of rotation is 0, the body is in equilibrium. Thus, according to the principle of moment in equilibrium, sum of the anti-clockwise moments is equal to sum of the clockwise moment. To understand, verification of the principle of moment is very important. Here, for this, we have to consider a meter rule, that means a meter scale horizontally from the fixed point, that means at the strong thread at O. As you can see in the picture 1.16, balances both the side AB on the meter rule. Then suspend some slotted weights W1. The meter rule may tilt at one side. Now adjust other slotted weights on the other side thread. Then you should see both should balance. Then we will come to the conclusion by seeing the distance between OA is equal to L1, OB is equal to L2, and the weight is acting W1 to turn clockwise, W2 to turn anti-clockwise. Then we will say clockwise moment of the weight W1 is equal to W1 into L1, anti-clockwise moment W2 is equal to W2 into L2 for